Welcome to the online lecture notes of Mathematics for Quantum Physics. My name is Michael Wimmer, and I will start with you the first topic today, namely complex numbers. This should be mostly a reminder of things that you already know. We will start with the basic definitions of complex numbers and basic operations, then talk about the most important complex functions, and finally discuss differentiation and integration. Each of those parts will be in a different video, and this video will be followed on the web page by written lecture notes. So if you want to look something up later, you can actually skip the video and go directly to the written part to find what you're looking for. Or if you prefer to learn by reading, you may skip these online videos completely and only read the lecture notes. All of our lecture notes will be structured like that. Note that sometimes in lecture notes we give links to more advanced topics. Those can be interesting to read, especially for people which are already very familiar with the things that we are talking about, but those will not be part of the examination. With that said, let's actually start with the topic. Let's start with the definition of a complex number. So a complex number Z is defined as x plus I times y, where x and y are ordinary real numbers, and I, that's the imaginary unit, and that one behaves to most degrees like a normal variable, but it has a special property that I squared equals to -1. Now, I said that I behaves like a normal variable in most regards. So what you can actually also do is you can also turn this around and write the complex number as x plus y times I. That is actually the same thing. Now, the first part of this complex number, x, that is called the real part of the complex number, whereas y, so the second part here, that is called the imaginary part. And there's also a notation for that. So we denote the real part of z as that, and that is x, and the imaginary part of z equals to y. Now, this is definition. We can also define additional operations on complex numbers. One of them that we'll use more often is the so-called complex conjugation. And the complex conjugate of a complex number is denoted as Z star. And that one is defined as x minus iy. So we flip the sign of the imaginary part of the complex number. So instead of plus iy, we have minus iy. A second thing that we can define for this complex number is we can define the absolute value. And that is defined as absolute value of z equals to square root of x squared plus y squared. So we see here that this definition of the absolute value that agrees if we plug in a real number, because then we just get, always just the absolute value because it's a square root of x squared. That's always a positive number. This is a generalization for the complex numbers. And we'll later see how we can actually visualize this absolute value when we introduce the complex plane. Now, having defined these complex numbers, what we actually want to do now is we want to do operations with these complex numbers. And in order to do that, we usually need more than one complex number. So we have now two complex numbers, Z1 equals x1 plus I y1, and Z2 equals to x2 plus I y2. And for these two complex numbers, we can now define, for example, the addition. So we have Z1 plus Z2. And as I told you, basically, you can treat this imaginary unit I just like a variable, and that's also what we can do here. So what we see here is that there is two terms without an I, so that is x1 plus x2. And then there's two terms that are next to the y1 and y next to the I, that's the y1 and the y2. So we collect those and we then have I y1 plus y2. So that is easy. Now we can also define multiplication of complex numbers. So let's do that. Let's do Z1 times Z2. And again, we just X this out. We see that because each of these complex numbers has 2 terms, we know that the product will have 4 terms. So we just have to take all of these terms together, and we start off with x1 times x2. Then we have also I y1 times I y2. So that gives us a plus I squared y1 y2. And then we have the cross terms, and those we collect as I times x1 y2 plus x2 y1. And now if we just think back how we defined the imaginary unit, we actually know that I squared equals to -1. So we can simplify this and instead have here a minus sign. So this is the formula for multiplying complex numbers together. There is one particular case that is interesting, and that is if we multiply z now with its complex conjugate. So if you remember how the complex conjugate was defined, that we have here, then we see that when we now apply this multiplication, that in this formula for the multiplication, the cross terms drop out. That's because there will be a minus sign here, and this term is actually the same. And additionally, we see that because of the minus sign in the complex conjugate, also here y1 and y2 have opposite signs, so that in total, we simply get x squared plus y squared, which we clearly recognize as absolute value squared. So these were the first operations, which are quite simple. Now let's go to a little bit more complicated one, that is division. So if we take the quotient of 2 complex numbers, say Z1 divided by Z2, then it's not immediately obvious what we should do, because we know that if you have a quotient which has variables in both denominator and numerator, we also know that you cannot easily simplify these expressions. But here, we can apply a trick because the complex numbers are more than just an expression with a variable. What we can do, we can multiply both the numerator and the denominator by the same number. And in particular, we want to multiply both of them with Z2 star, the complex conjugate of Z2. And the reason to do that is that if we do that, then the denominator becomes real. And then we know what to do, because then we can just divide the imaginary and the real part of the numerator by that real number. And if we just X that out, then we see that the expression that we get, so the denominator, that is simply x2 squared plus y squared, so just a real number. And in the numerator, we get x1, x2 plus y1, y2. We have a plus sign here because here we have the complex conjugate. And then here, and then for the cross terms, we get I times x2, y1 minus x1, y2. So this is a generic formula for calculating the quotient of 2 complex numbers. Now, in practice, actually, I never remember this formula, but I just remember that there's this trick of multiplying the denominator with the complex conjugate, because then, then it basically boils down back to multiplication, which is easy. And let's just do that now for a particular example. So in the example, I want to calculate 1 plus I2 divided by 1 minus I2. And as I just told you, now the trick is to multiply both the numerator and the denominator with the complex conjugate of this number here. So what we need to do is we need to multiply both with 1 plus I2. So we have 1 plus I2 times 1 plus I2 divided by 1 minus I2 times 1 plus I2. Now for the denominator, we get 1 squared plus 2 squared. And for the numerator, we simply have 1 plus I2 squared. And that gives me a 1 plus I4 plus I2 squared, which is, as we know, because I squared is equals to -1, is -4. So now collecting all the purely real numbers and the purely imaginary numbers together, we find that the real part is 1 minus 4, that's -3 divided by 5. And then we have plus I times 4 divided by 5. And this is the easiest way, in my opinion, to calculate these quotients. Now, these are, abstract operations. And, basically, we just define them in a purely mathematical way. It's always also interesting or useful to actually think about whether we can visualize these operations. And, when you have real numbers, then, from school that you were visualizing operations on the line of real numbers, like addition is, jumping along the line of real numbers. Now, for complex numbers, we have a real and an imaginary part. So the natural way of visualizing a complex number is by using the complex plane. So a two-dimensional object, so the plane in 2 dimensions. And in this case, when we have a complex number z, that is a vector in this 2D plane with, and this 2D plane is spanned by both the real part of z and the imaginary part of z. And the coordinate in the real part, that's simply x, so that's the real part of z, and y, that's the imaginary part of z. So you see that there is a very natural visualization. And we also see here now, because z is a vector in this representation, that the absolute value of z, that is the length of the vector. So we see that this also has a natural visualization. And for example, the complex conjugation, that would correspond to flipping the, so the complex conjugation, what you do is you flip y to minus y. So you would actually flip this vector along the real axis down, as I just showed. Now, when we want to visualize operations, then we can also do that. And in particular, what's very easy to visualize is addition of 2 complex numbers. And what I have here is now 2 complex numbers, Z1 and Z2, each represented by a vector in this complex plane. And actually, if you just think back how we did the addition, we added simply the real parts together and the imaginary parts together, and that corresponds to the x and y coordinate here. So addition of complex numbers simply corresponds to addition of vectors in this complex plane. So when we want to add them, what we basically have to do is we have to take this vector here. And what we need to do now is we need to just put this vector on the tip of the other vector, and the resulting vector, that is the sum Z1 and Z2. Now, you can do this visualization for basically all the operations, but it turns out that for many of these operations, such as multiplication or also division, it's actually easier if one goes into a different representation of these complex numbers, the so-called polar form. And that we'll do in the next video, because in order to go there, we first need to define complex functions, and in particular, the complex exponential function.